In the second part of the quality control, I will describe the defects that occur typically in adhesive joints and describe the destructive tests available to assess the quality of the joint. So let's go to the second part of quality control. The first part was more about materials. The second part is about bonded structures, but about the destructive tests. Let's start with the destructive tests, but before we start with the type of defects that we can have in a joint. And unfortunately, there are of many types. So what can you have? Well, you have some that are very, very obvious. For example, a big void in the middle or at the interface because simply you didn't put enough adhesive. You can have porosity because you have an adhesive that cures by condensation and you didn't have enough, or you didn't apply enough pressure, or you are using a film adhesive that tends to be porous. You can have a poor cure because you didn't mix properly the adhesive, or you didn't wait long enough for the adhesive to cure. You might have a crack because of residual stresses, because of the shrinkage of the adhesive, or because you are using dissimilar materials and the adhesive cannot withstand well the differences in coefficients of thermal expansions. So many defects. There is one that is particularly bad, I leave it for the end, which is weak adhesion. There is adhesion, there is contact between the adhesive and the substrate, but not with the strength that you want. And this one is particularly bad because you cannot detect, or very, very difficult to detect. All of the rest, it's all right. This one, very, very difficult and a big nightmare. And that's one of the reasons why it's not even more used in many industries, or with a bit of mistrust because of this particular situation. Let's see the destructive test. So we know that we have these defects. One way to check if there is defect or not is to test, obviously, destructive test. We have seen so far one test, very common. The overwhelming majority of the tests done is that test, which is the single-up joint. Okay, but we don't only use single-up joints to assess the quality of the joint. There are also peel tests. Even though peel is the enemy of adhesive joints, still you need to test in peel to check the behavior in that loading mode. And it's a very good test also to assess the adhesion strength of the adhesive to the substrate. And as you can see, there are three main peel tests: the T-peel, floating roller peel, and climbing drum peel, especially to assess the adhesion between the skin to the core of composite sandwich structures. Peel in general is associated to elastic adhesives. If you use a single-up joint, typically the failure will be abrupt. But if you test a peel joint with an elastic adhesive, typically the failure will be progressive and there will be a plateau during the test, as indicated here. Also associated to elastic adhesive is the adhesive thickness that is different, its effect, than with rigid adhesive. With rigid adhesives, you don't want very thick bond lines, you want the thinnest bond line. But with elastic adhesives, you like thick bond lines because the adhesive can spread the load over a big area, and the thicker, the better it can do that, the spreading of the load over a big area. You have laboratory destructive tests. Of course, the ultimate test is the proof test on a real structure. You have here an example of a real test. In this case, it's the crash test. It's a very common test in the automotive industry, but of course, this is extremely expensive. You are not going to do that in all the structures. Another test that is common for the bus industry is the rollover test. So you put your bus in a platform, then you roll over, it falls down on the ground, and if it doesn't lose its integrity, then you are right. And there are other proof tests for other industries. For example, the aeronautical industry also have this kind of test. After you destroy the joint or the structure, it's always good to analyze the failure mode. See if you have a nice cohesive failure. As you know already, you don't like adhesive failure or interfacial failure. Many times, let me show you, you have failures that apparently take place at the interface, but in fact, if you look like this example, you see, it's very clear that you have adhesive on one side and you don't have adhesive on the other side. So that indicates that it's an adhesive failure. But if you analyze this surface with naked eye, apparently it's adhesive failure. But if you analyze in scanning electron microscopy, many times we realize that in fact it's not an adhesive failure, it's more a mixed failure, and sometimes you have adhesive all over. In this case, you see it's a mixture of adhesive, these parts are adhesive, and this part is metal, so mixture of adhesive and cohesive failure. You can also use scanning electron microscopy to understand if you had a more ductile or more brittle failure. The aspect of the adhesive will be different. A brittle is smoother than a ductile, which is very rough, as shown here. If you still have doubts, you can make a chemical analysis. You have this attached to scanning electron microscopy, for example, XPS, and then you point to the area which you want to analyze the chemical composition, and then this will clarify if it's if it's an area rich in carbon, that means probably that it's adhesive. It's poor in carbon, that means probably it's metal. Atomic force microscopy, we have already talked about that. We have talked about that in the initial quality control of the substrate, but you can also use it after the failure to understand what's the surface topography and relate to a more brittle or a more ductile behavior. So that's for the destructive tests of bonding structures. Now we are going to see non-destructive tests in the next module.